Good day to all of you. Today we begin a new topic, control and remedial measures at contaminated sites. So if a site has become contaminated either by waste dumps or slurry ponds on top of it, but in many cases by several other causes, then what do we do at these sites? This will be the topic of discussion for the next 2 lectures. And remember, we will only focus on the role of geotechnical engineering, because control and remediation of contaminated sites requires an understanding of the contaminants, how they can be removed. Now these may be issues of chemistry or chemical reactions or biochemistry or biochemical reactions. So we definitely need an interdisciplinary approach to solve these problems, but we have to help all the chemistry and the chemical engineers and the biochemical engineers reach the soil, reach the groundwater, and then undertake the processes of cleanup. So let us see what we are going to do today. So we just quickly recall that there are 2 words we are using: control and remediation. Control is containing the contamination, means we stop the further spreading of the contamination. At a site, when you reach, there would be a source of contamination and there is uncontrolled release. So we undertake control measures to prevent further spread of contamination in the affected area. Remediation, of course, is that we bring back that site to its original condition, that is before the source of contamination was placed on that site. Control is less costly than remediation. Control is usually the first step. I mean, immediately after you recognize that a site is contaminated, you would like to take control measures very early so that there is no further spreading by the time you come up with a remediation plan. The word rehabilitation is sometimes used as reflecting remediation. Sometimes it is used reflecting control, or a bit of both. So we will be using the words control and remediation in the next 2 lectures. When you have a site which is reported to be contaminated, and since this is all subsurface contamination, you will get some either some visual reports, or you will get some groundwater contamination problems from a receptor. Then the question which comes to our mind is the site not contaminated? Is it probably contaminated, or is it definitely contaminated? Suppose you start getting contaminated groundwater in your hand pump. So it's not that the adjacent soil will be contaminated. It's possible that the soil or the source is far away and the contaminants are leaching from that source into the groundwater, and in the groundwater there will be high permeability zones and low permeability zones, and maybe the contaminated groundwater is traveling in the high permeability zone. So once you have a reported incidence, you have to first check, is the site contaminated, is it not contaminated, or is it probably contaminated? Now see, it seems very simple that I can go and say that site A is contaminated. The first question is, to what extent is it contaminated in plan, and to what extent is it contaminated at depth? So that requires very detailed investigation. Before you attempt to quantify whether it is completely contaminated in a particular zone, you have to do preliminary testing to establish whether the site is not contaminated or probably contaminated. So today in India, 3 classifications exist. You may get a report, site may not be contaminated. You may get a report, and from the preliminary data you may say it is probably contaminated, and then after doing detailed studies you can call it a contaminated site. When you want to call a site contaminated, you need some standards to measure the contaminant levels. So each country has national standards for permissible limits on concentration of contaminants, whether it is heavy metals, whether it is dioxins, whether it is pesticides. So all countries have national standards for permissible limits. And you have to compare the existing levels of the contaminant with respect to the permissible limits. India does not have soil standards today. And the process of coming up with national standards for soil contaminants is currently underway in the Ministry of Environment and Forests. But we have other country standards. So if you don't have data from India, you can look at standards from other countries. However, if a contaminant level is high, doesn't necessarily mean the site is contaminated. It is possible that the background levels in that region are high anyways. So what you have to compare is, suppose there is a doubt in your mind that there is a lot of high level of arsenic being reported. Is it something which has been artificially introduced into the ground, or is it that this is an area which had geologically some source of arsenic which caused the arsenic levels to be high? Therefore, the first step whenever you get a contaminated site input is to look at background concentrations. Move away from that site, move 20 kilometers away from the site, and go and pick up some samples from all around. So you first establish the background concentrations of that particular contaminant of concern. If you find that the background concentrations are low, and if you find that they are higher than the permissible limits of the standards, then you have to go to a screening stage. That means you can say that it is higher than the screening level, therefore I need detailed investigations to look at the action that we have to take. And if the concentrations are beyond a response level, that means it is mandatory to take action. So you have a soil standard which says that X milligram per liter is the permitted concentration. You find that you have got a value Y. The value Y which you have got may match the background concentration. That means there is nothing in that site which has induced it to become higher. It may not match the background concentration. It may not match the background concentration, and it may be higher. Then you have to see whether it is higher than the screening level. If Y is higher than X, that means we have to now establish in what area is the Y greater than X. Is it a local 1 or 2 sample reading, or is it that over 100 meters by 100 meters to 3 meters depth you've got some problem? So you do further investigations after your level of contaminant exceeds the background and the screening levels. And if the level is very high, that means you do detailed investigations and you get even higher values, then these are called response level. That means you have to take action to bring the contamination levels down. So you have a background concentration, a screening level, and a response level. So in a country standard, you may have 2 levels reported to you: screening and response. So typically, when you got some information from any site, either telephonically or through an email or through a letter, you have to do a site walkover and data collection. You have to find out the history of that site, what all may have been dumped on it, and then you may do some preliminary site investigations. Preliminary site investigations may be picking up samples from a local well, a hand pump, a tube well, and picking up a few shallow soil samples using hand augers. So they just get an idea of what's happening at the surface and at the nearby wells. If you find that the levels are elevated, then you will go for detailed investigations. Now, detailed investigations means, as I have said earlier, that you've got a report that this is the point in which there is a high level of contaminant. You have to first establish the boundaries in plan and depth. This is in plan, let me say. So I need to first do a coarse grid investigation as to how far are the background levels elevated. And when I can find out that, okay, it's elevated here, it is elevated here, here, and here, and here, then you feel that, okay, this is the area requiring further investigation. So now you may use a finer grid to be able to earmark what is happening. So you may do more tests to identify. And you'll have to continue to do it till you get no contaminants around it. So you need to have no contaminants far away so that. So this way I may be able to say that this zone is contaminated in plan. Then the next issue is to what depth is it contaminated. Then this person had reported you that the hand pump was picking up water from this place. So once you have identified the locations, then you might pick up samples from various depths. And then you may be able to say that my plume is something like that. So you need to be able to do detailed investigations to be able to quantify the amount of contamination. Once you know, is it contaminated at the top few meters? Is the groundwater contaminated down to 25 meters? Then your strategies for solving the problem will come. So detailed site investigation will tell you how far the contamination is spread. You have to then do feasibility studies as to how you can remediate the problem. And remediation technologies are not standardized. There are a few which we will discuss, but they are being developed ever so often. And remediation technology will be contaminant dependent. So you may have thousands of contaminants. So for a particular contaminant, you may need oxidation, you may need neutralization for another one, you may need volatilization for another one. So you may have, depending on the type of contaminant, different technologies. So at the stage after detailed site investigation, you look at the technologies which are useful for that contaminant. You have to compare the alternatives. Some of these may not even be proven because this may be a new soil condition. So you have to, after comparing the alternatives, look at the cost options, and with the cost options, you select the technology. Once you have selected the technology, then you'll have to do remedial design. Suppose your technology is that I will extract the groundwater and treat it. Then how many wells? What is the spacing? What is the depth of wells? That is what you will do in remedial design, so that you can work out exactly what you have to install, and when the water comes out, what is the type of treatment plant? Am I going to use reverse osmosis? Am I going to use a biological process? That's remedial design. And because soil is so different from one place to another, you first have to do a pilot study. Many of these technologies are on the cutting edge. You have to do pilot studies. Is what you have chosen effective? So you will first do pilot studies on a small plot of land, apply your solution there and see if it is effective. Once you find that it is effective, then you go for remedial action. That means now you do a full-scale application of the technology and look at the remediation. And because it's a contaminated site, monitoring will be done right from the very beginning, all through remedial action, and post-remedial action as well. That means this is going to be a totally instrumented site where data, what were the levels before, what are the levels 1 month after, 1 year after, 5 years after, 10 years after, what are the contaminant levels that will have to be monitored. So this is the full planning and implementation methodology. And do remember that no single solution is there which I can hand out over to you and say this can be adopted. Strategies are simple. If the source is small and if you have been able to identify it, remove the source, because first is what is causing the contamination. You have removed it, where does it go? You dig it out, but where does it go? Well, either it will go to a landfill, a hazardous waste landfill, or whatever it appropriate, or you'll have to treat and transform the source. Then along with the source, the soil and groundwater will also have to be treated. So suppose the source was somewhere here, or maybe it was partly below the ground, partly above the ground. So this has to be tackled, and all this zone has to be tackled. So is it an issue of tackling the liquid phase? Is it an issue of tackling the solid phase? Or is it an issue of tackling the 3 phase? Because there may be a vadose zone in between as well. So you will remove the source, treat the source or encapsulate it or transform it. You'll treat the soil and you'll treat the groundwater. This is easy for very small site contaminations, and believe me, there are several small sites. You know, in industrial areas you'll find that somebody has gone and placed some chromium sludge on a open plot of land, and the plot of land may be only 200 square meters. Okay, plot of land may only be 15 meters by 15 meters, and the contamination may have gone down. So you may have to remove that sludge which is on the top. You'll have to see how many meters the soil has got, the chromium has traveled down to. You may have to, you might want to remove the soil. It may not have reached the groundwater yet, and if it has reached the groundwater, you might want to do pump and treat. That's if it's small. Suppose it is big. You can try and remove the source. Means, let me say, suppose the source is not very big, but the contamination spread is big. Okay? Then you may still be able to remove the source. But now, since the contamination is very big, you can't dig up the soil and treat the soil. You can't dig up the water and treat the water. It may take months and years to extract the groundwater and treat it. So then what you do is, you know that you cannot treat such a large mass. So you remove the source, you cut off the pathways, you might make a vertical barrier around it, and protect the receptor. You may say that no groundwater wells can be placed in this zone, and if there are groundwater wells, you may seal them so that nobody can use them, and allow that land only for specific use. That means your groundwater supply will now come over surface water. You can use the ground surface, but you can't use anything from below the ground. So strategy 1, remove source, treat soil, treat groundwater for small sites. Strategy 2, source is small, remove it, but the spread is large, cut off the pathways, nothing further should reach. In that zone, say, nobody is allowed, nothing can be done. Protect the receptor and allow for specific use only. If the source is very large, like if you have a hazardous waste dump, and let us say hazardous waste dump is 300 meters by 300 meters, now you've got a problem. You can remove the source, eventually you have to put it in a landfill, right? So you have to construct a new landfill either at the same area or nearby, and you have to take the whole source away. But till you can do that, because it may take some time, you might want to cap the source so that further release of contaminants is reduced. So when the source is large, cap the source and do everything else. Do the cutoffs, protect the receptors, and allow specific use only. So, it is a graded response depending on the kind of problem that you have. And as far as the land use is concerned, you have some 2 or 3 options. Land use can continue to be used as original, or it can be used for limited purposes only, or it cannot be used at all. So, it is very simple to say, okay, you can't use this land, but if it is a large tract of land, to suddenly tell all the industries around it and the villages around it that, look, you can't use this land, may be incorrect. But you can specifically say no groundwater wells here, no digging here, you can't remove any soil from here for purpose of making something else, but you can use the top of the surface. We are monitoring that there are no gaseous emissions and volatile organic compounds coming out. So, that may be for limited purpose. And of course, to allow it to be used for all purpose, you have to have complete remediation. Complete remediation is a very, very expensive exercise. It takes a lot of time. So, many people look at intermediate solutions. So, just to recollect, we have done this before. Your source of contamination can be the solid waste dumps, which we have done a lot about. People may have buried their waste in trenches or put drums at a site and buried it. The sludge coming out of a small effluent treatment plant of a factory may have been applied on land, or it may have been filled in low-lying areas. You may have a liquid waste pond which is just leaking, or a reservoir. You may have a factory discharging its effluent in a no man's land adjacent to the wall. You may have buried drums of liquid waste. Here we are talking of buried drums of solid waste, or buried tanks which are leaking like petrol tanks. We may have leaking pipelines. In the past, some industries were injecting their wastewater into the ground. Now it is not allowed. There may be some accidental spills, and there may be agricultural applications of pesticides and other compounds. So, these are all the sources, and if you look through literature, you have to prepare a typology diagram. The typology diagram must state what you understand is the source. Is it a solid phase contamination? So, was the source originally solid or liquid? That is what you must say. If it is solid, one of the ways it is contaminated, it has been mixed with the local soil. That means you had undulating ground, you had some sludge, you came and mixed it and covered it so that nobody would find out. And that's given a symbol like this, and it is called contaminated material mixed with soil. Sometimes it is very well defined. I mean, people actually make big trenches and pits and they put their waste in it, or you may have a mound at the top. But these are well defined. So, still it is solid phase. That means the original contaminant is coming from the solid phase. So, you may have an embankment, you may have a small heap, a mound, or a pit which may have been covered with soil, but the boundaries are now well defined. You can also have irregular storage of contaminant material. You have a plot of land, a football field or half a football field. One day somebody threw the waste at one end, another day somebody threw another waste at another end. It may be an irregular storage, and this kind of symbol is used. Material added through agricultural activities, we are always doing some modifications at the top. We are using pesticides and other kinds of pest control chemicals. They may be excessive. So, they will get mixed at the very top layer of the soil, very, very thin top layer of the soil. You may have atmospheric deposition of emissions. You have a waste to energy plant, or you have got a thermal power plant, the ash is coming out of it, and the ash is settling with time. You will find a thin layer. So, you may have some atmospheric deposition of emissions, or you may even have a site washout. You have a slurry pond, embankment breaks, and the entire ash comes out and floods your fields. So, basically the contamination is coming from the solid phase, and these are some of the standard diagrams which are used in the contaminated sites program. If it is, there is one more solid phase which is actually underwater. See, all these solid waste were solids on soil, solids on soil, solids on soil, but there is underwater deposition. So, most of the canals, most of the surface water drains, eventually you will have a thick black deposited material. Worldwide, it is known that it contains the maximum number of contaminants. The water is passing by, all the total suspended solids or others are falling. These sediments or sludges are either treated after excavation or they are put in hazardous waste landfill. So it is also solid phase contamination, but it is underwater. So you have underwater sediment containing contaminants. So you will have this kind of a contaminant. The other typology is liquid phase, right? You may be having some liquid coming out of some industrial processes which is leaking at the site itself. Or you have stored the liquid either in a reservoir or in drums or in underground buried tanks, or your liquid has leaked through pipelines, or you have had accident spills. So these are the standard diagrams which are used for defining the typology. Sometimes you are having now non-aqueous liquids like in petrol stations, and there are a lot of them. So you may have DNAPL, dense non-aqueous phase liquid. That means this will come into the ground. This is the groundwater table level. It will go and sit at the bottom of the groundwater table level. Or you may have LNAPL, that is something which is lighter than water, then that will float. It won't mix with the water, it's immiscible, but it will float. So it's DNAPL and LNAPL are the ones which are observed at various hydrocarbon processing stations or the petroleum stations. And finally, you may have many sources contributing to contamination in the groundwater. So this is the typology which is now universally recognized for the sources of contamination. The first results from a World Bank aided project are coming out now. 300 probable contaminated sites have been identified in India. The number is likely to become much bigger. But the results from the 300 probably contaminated sites in India, and these are not including the big municipal solid waste dumps and the hazardous waste dumps, which are also contaminated sites. But what do you find? What kind of contamination is being reported in India? 70 sites have chromium, 50 have excessive lead, some have excessive cadmium, arsenic, mercury, and so on and so forth, fluorides, VOCs, heavy metals not specified, pesticides, PCBs, nickel, asbestos, and so on and so forth. So these are 300 probable contaminated sites in India. The list is ever expanding, and some of these will become contaminated after detailed studies, and some of them will be classified as not contaminated because they are below the background levels. So what do? We said we can either do control or we can do remediation. Control comes back and brings us back to a very similar situation that we had. You can have covers or caps. You can have vertical barriers. You can have combinations of covers and caps with vertical barriers. Base sealing is expensive, can be done, but is usually not adopted. And sometimes these may be in conjunction with pump and treat. This is where geotech engineers have a lot of role to play. If one goes for remediation, it's a different problem altogether. You have to treat the source, you have to treat the soil, you have to treat the pore gas, the gas in the pore space, you have to treat the pore fluid, and you have to treat the groundwater. Pore fluid may not be groundwater, it can be some other fluid. And this treatment can be done after excavation or extraction, that is called ex situ, or you might want to do the treatment in situ. So we'll look at these two separately. So let's first come to control. So control is very similar to the covers that we have done. You can have local soil cover, you can have municipal solid waste cover, you can have hazardous cover, or you can have paving over geomembranes and others. The most often adopted cover is the hazardous waste cover. The most often adopted cover as a solution is the hazardous waste cover. Sometimes you will also put a paving over geomembrane, but the tendency is to cover it in a manner that further release is reduced. If you cannot remove the source, you have to cover it in a manner that the further release is reduced. So here we don't have much to do. But the new thing that we are now addressing are vertical barriers. And let's go back to design of dams, where we were preventing seepage from the base of a dam. So if I am constructing a dam here, and that's my bedrock. So why I'm bothered about seepage through the dam and also seepage beneath it if this is pervious. So in the dam, to prevent seepage, I put a core, a clay core, right? And this line disappears, it comes here now. So we've been dealing with this for many years. What do we do below the dam if it's got a pervious bed? How do we prevent the seepage from going from beneath the dam? Well, first choice is not cut-off wall. First choice is a cut-off trench. Making cut-off walls is difficult. You just see a dam is sitting on bouldery strata and you want to make a vertical wall in a bouldery strata. It's an expensive exercise. So first they say, can I excavate it? And if I can excavate, can I do open excavation and can I come back in layers and put clay in it? So this is the standard traditional cut-off trench. The cut-off trench may be a few meters deep. 0, 3, 5, 7. You have to cut it at slope, so you have to have the available width at the top. Water may still seep through this or no? Is this rock going to be impermeable? Is soil likely to be underlain by impermeable rock or more fractured and disintegrated and then later on competent rock? So most of the interfaces between soil and rock are not hard rock. They all have joints and fissures and they are pretty permeable. So you will have some kind of jointing pattern and then this will be competent rock at the bottom. So if I stop the water here and if I stop the water here, water still wants to go through the rock. So what do we do? What do we do when we want to make an impervious barrier in rock? We do grouting, cement grouting. Why don't we do grouting in the soil? No. Grout will also flow in the fissures of the rock. If there are cases, then you put grout in the rock, it will come out 1 kilometer downstream. If you are pumping grout here, it's coming out 1 kilometer on the other side because all connected at the bottom. So in soils, it's difficult to pump in cement grout unless it's pure gravel and sand. If it has any fines, the pumping is difficult. In rock, pumping is simpler because the fissures tend to be interconnected and the grout goes in the direction of flow which is possible. In soil, if you have silt, no grout can travel, cement grout cannot travel. If you have silty sand, cement grout will not travel. Only when you have coarse sand and gravel will cement grout travel. So what we do in dams is we make a grout curtain, and grout curtain may be 3 rows of grout holes. Now I have an impervious barrier. So the first thing that you see here is, of course, when the location of the rock is deep below, when the location of the, instead of this situation, suppose my situation was, this is the base of the dam and my rock is here. Now making a 20-meter deep cut-off trench is very difficult, right? So I have the option of grouting or I have the option of making a vertical diaphragm wall, a vertical cut-off wall. So when the rock is deep below and my dam is way up there, then I have a tendency to put a vertical cut-off wall. I don't do grouting in soil because it's not simple to do grouting in soil. I might want to grout something vertically, it may not get grouted vertically and the grout may not penetrate into this. So I will make a vertical cut-off wall and then below that may be the grout curtain. What is the vertical cut-off wall made of? Cement, concrete, soil, plastic concrete, PVC. The vertical cut-off wall is not a diaphragm wall which is retaining earth behind it, like for Calcutta Metro. So it's typically not an RCC wall. It will be a plastic concrete wall or it will be a soil, cement, clay mix wall. It's an impervious wall. It's not a structural member. Okay? So we'll see this as we go along. So vertical barriers are compacted clay in trenches when the thickness to the impervious strata is low. it can be cut-off walls. Now the word that you're going to come again and again is slurry walls. They call them slurry walls. Everybody seems to think they are made of slurry. They are not made of slurry. They are only stabilized with bentonite slurry. So please don't think that a slurry wall is made of slurry. Okay? So you are going to have cut-off walls made of clay or soil bentonite or soil cement bentonite or cement bentonite or plastic concrete or composite. So because concrete is often attacked by sulfates, you don't tend to use concrete walls unless you can preclude that none of the chemicals in the waste in the contaminated site will affect the concrete. You want flexible walls, so you typically tend to use a soil wall, clay or soil plus bentonite or bentonite plus cement or soil plus bentonite and cement. We can have grouted barriers and we can have deep mixed barriers, and we can also put sheet piles. But cut-off walls are the first and most cost effective solutions. So this is the contaminated site. You have shallow contamination, you have low permeability strata at shallow depth. If this depth is 0 to 5 meters, it's a good enough way of isolating the contaminated site. So this is the cut-off trench of you'll have to send the roller in or the compaction device into this and make the cut-off trench. Rarely you get very shallow, low permeability strata at very shallow depth, but nevertheless this is one of the solutions which exist. When you are starting to make cut-off walls, which they call slurry walls, the wall can be made of clay. It can be, if clay is available locally, it will be made of clay or nearby. If it is not available, then you come back to what we were doing for amended soil barriers, soil plus bentonite, or it may be made of soil plus bentonite plus cement. You might want to give some strength, additional strength to the wall. We'll do an example. Or it can be made of soil plus bentonite, and you may want a double assurance that nothing is going to go past. You might put a geomembrane inside that. And there may be special sheet pile walls. There may be special sheet pile walls. There's another word here, reactive permeable walls or reactive permeable barriers. This is something on which I want a self-study by you. What are reactive permeable walls or reactive permeable barriers? These are not barriers, these are pervious walls. And let me give you the thought is very simple. In all the walls, we are trying to keep the contaminated water within the walls, right? In reactive barriers, you are making the wall of a material which has a chemical which will react with that contaminant and allow only treated water to go through. So it's a very specific solution for a very specific type of contaminant. You can't have a magical chemical which will put in a wall. On one side is contaminated water, on the other side is drinking water. But if you have one type, which you may be in your one-page write-up, so I want your one-page write-up to be one diagram of half a page and one paragraph on where is this kind of solution used. Okay? Half a page diagram will just tell you how the wall is made. But we are going to look at this clay and soil and bentonite and soil and bentonite and cement walls. So let us say this is the contaminated site in plan. Okay? So the philosophy is, can I put a wall or an impervious wall around it so that the water can bypass it? I have my groundwater flow in this direction. Can I get the groundwater to bypass the wall? So this is the contaminated site, and this is a circumferential cut-off wall. Assume it to be made of low permeability material. In section, this is what it will look like. It will have a cover at the top so that no more release of contaminants cannot take place, and it will have vertical cut-off walls. Now how deep do they go? Theoretically, they should go to an impermeable strata. Those are called key-in cut-off wall. You've keyed them in. But suppose the impervious strata is 100 meters deep. Then you make a hanging wall. Still remember, you would have made a wall all around it, and it is pretty deep, and the fresh groundwater is passing by and not reaching the top. So this is what is done. You excavate a trench 0.5 to 1.5 meter wide. How do you excavate? You normally use an excavator, a backhoe. You've seen this device? What is a backhoe? You can excavate with the backhoe, and typically backhoes can have extended arms from 10 to 12 meters deep, so they can dig very deep. This trench is stabilized with bentonite slurry. Imported clay or soil mixed with bentonite are made in the form of high slump material. You remember high slump concrete? Yeah. The idea is you should be able to put this material in the trench and it should be able to slump and spread by itself. So you have to add enough water to your clay or to the mix of bentonite with the excavated soil and make a high slump mixture. Backfill this into the trench and the slurry will come out. Keyed in wall reaches the low permeability stratum, but hanging wall does not, and it is used in conjunction with pump and treat. So you excavate a trench using an excavator, fully excavated trench, and it is stabilized with bentonite slurry, 5% bentonite, and then you start sending in your high slump material. How do I send it will become apparent. This slurry keeps on coming out now, and that's your final wall. This is the way the operation goes. This is the cutoff wall being constructed. Okay. This is the unexcavated soil. Your backhoe is making this trench. All right. The spoils are coming here. If you are getting clay from outside, you bring the clay and slump it forward from the sides. Okay. This is high slump material. If you don't have enough clay, you take this trench spoils and mix it with bentonite, 5 to 10% bentonite, and deposit it. The slurry keeps on coming out. So the trench is excavated and proceeds in this direction. And you can see that normally, typically, you will get 10 to the power of minus 7 centimeters per second with about 5% bentonite. We have done this before. Sometimes you want even higher impermeability. Then in your wall you might put a geomembrane. And there are these geomembrane sheets which can, there are special arrangements by which the machine can make them go vertically into the bentonite, into the soil wall or the soil plus bentonite wall. You can also make overlapping cement columns, deep mixed columns. We've done this in ground improvement. Again, rarely used, but if you want a wall made of overlapping columns, then you can have deep mixed augers. There are 3 augers which you are operating, and they can overlap and make a deep mixed vertical wall. But by and large, the wall which is used very often is the clay wall or the soil plus bentonite wall. You might want to put a subsurface drain in conjunction with this. A subsurface drain is something in which perforated pipes are buried in trenches and backfilled with coarse material. Water flows by gravity to the collection sump and is pumped out. So instead of making an impermeable wall, I make a pervious wall. If the plume is coming, I put a perforated pipe at the bottom. Water will flow into this. I have to continuously pump it out at some sump. So sometimes you can use subsurface drains to augment your barrier walls to reduce the depth of water table. So far we have seen how to contain, but we have to actually solve the problem of bringing it back to its original condition. That means we have to treat now. We have to treat the source, we have to treat the soil, we have to treat the pore gas, we have to treat the pore fluid, and we have to treat the groundwater. And we can do it ex situ or in situ. And we will take it up in our next class. But the first action that we take always is control. 1, control is cheaper. 2, control can be effected relatively quickly. And at least you are at peace that the further spread of contamination is not taking place. So apart from the covers that we have done, the major role of geotechnical engineers is to make a vertical wall. And in the next lecture, I will try and give you a case study example as to how we put a proposed cutoff wall around a tailings pond. So we'll stop here. And if you have any questions on vertical barriers, especially how to construct it, the most important thing is how do you construct barriers. Now suppose you want to make a vertical cutoff wall 30 meters deep, and you have an excavator whose arm can only go 12 meters of it. How are you going to make a vertical cutoff wall 30 meters deep? We need trench cutters. We have to use the same equipment by which we make diaphragm walls. And if you remember last time I had told you that trench cutters look like this. These are devices where these rotate and they cut a trench, and you are using reverse mud circulation. Instead of putting in the slurry, as they cut, you are sending the slurry up the pipeline. So you have to use trench cutters if you have to make deeper walls than 10 to 12 to 15 meters. And these trench cutters are the same that are used for making diaphragm walls for underground construction, like in metros and other underground openings. Any other questions? Subsurface drainage, right.
On this side we have some,
Okay. So there is a waste, there is a contaminated plume. My traditional solution is, let me put a cutoff wall here. We have to do something to this contaminated water. I can do two things. I can do pump and treat, or I can make a continuous pervious trench around it. If you put pump and treat, you have to put the pumps at very close locations in plan, say a few meters away. You can take out the water, treat it and re-inject it. So the diagram which was shown was, it was having a subsurface drain here. Is this the one you are talking of? So the idea is still that this water must get caught, pumped out and treated.
sir, I'm more concerned about the settlements, sir. What will be the settlements, and if we have a gapping, it will.
You are worried about the settlement of the surface because of these cuts that we are making?
When the water will go down.
So the design is not only of drawdown, it's also of injection wells. So when you do the design, the question that is being asked is that when we do all this pump and treat, or when we do the subsurface drainage, the water is taken out, then because of increase in effective stresses, settlements will occur at the surface. Answer is yes, they will occur. The question is, do we do very massive drawdowns? The answer is no, we do limited drawdowns. However, in the next lecture we will see we also put injection wells simultaneously. That means water is being extracted, treated and injected back. So you try to keep the level of the groundwater table about the same as what it was originally, or the drawdown may be very limited. So it's a mix of taking out and injecting. So even if you are putting a subsurface drain, water is not going to come out till you take it out from a sump. When you take it out, then you have to put in that much water back into the system. Okay? So we'll stop here and look at remediation in the next lecture. Thank you. Have a good day.